Hello everyone, my name is Stefanos Baziotis, and in this presentation I'm going to be talking about program synthesis. This is a talk I gave at the compiler meetup at UIUC, and I had a request to record and upload it, so after fixing a couple of mistakes, here we go. This is an overview of the talk. First, we're going to talk about Hoare logic. We're actually going to go a little bit deep into that. Then we're going to talk a little bit more about Hoare logic, talking about loops and verification conditions. And then we're going to use a program synthesizer to synthesize loop invariants. The way to think about this overview is that unless we do parts 1 and 2, part 3 is not going to make a lot of sense. Basically, we're not going to understand what we're trying to achieve. And finally, we're going to talk about CounterExample-Guided inductive synthesis, CEGIS, which is the most popular algorithm in program synthesis. Now, I want to say a couple of things about this presentation. First, it's supposed to be kind of self-contained. That's why I'm doing Hoare logic here. So, with a basic understanding of programming and logic, you should be able to just watch this without needing to reference external material much. The second thing involves CEGIS. And CEGIS is this very popular algorithm. It's much more than just a concrete algorithm. It's sort of a paradigm, a way of thinking. And because of that, a lot of people present the paradigm very vaguely. And at least when I was starting out with program synthesis, it was a little bit hard to understand like how you can instantiate this paradigm. Like, okay, I get the vague idea, but how does it work? So here we're actually going to go into very concrete details of how you instantiate CEGIS. We're going to see the original instantiation, which was from Armando Solar Lezama's thesis, the person who kind of rejuvenated program synthesis. So I'm going to use a lot of content from his thesis, and so we're going to go pretty deep into that, which I think is interesting. So with that, let's get started. Now what I'm going to do is I'm going to go ahead and remove myself from the frame because I'm going to be taking a big part of the screen. Okay, so let's start with Hoare logic. Now Hoare logic, the basic element is a Hoare triple. So let's define that. Now I want to say I don't generally like reading slides, but definitions are kind of important. So I'm actually going to read them aloud, and then I'm just going to be commenting on them. So Hoare triple has 3 elements. It has 2 logical assertions, A and B, one before, and then an execution of a command, and one after. And of course, it has the command itself. And it means that if command begins execution in a state satisfying assertion A, and if command eventually terminates in some final state, then that final state will satisfy assertion B. Okay, so first of all, A is called a precondition and B is called a postcondition. What the triple says is that if you start somewhere where A is true and you execute command, you're going to get somewhere where B is true. But there are some important details here. First of all, A and B are not states. So if you are familiar with operational semantics, if you're not, it doesn't matter. But if you are, you tend to think of semantics of programs as kind of state transformers, where you start with some state and then the program is in some other state after executing the command. But here, we're not thinking exactly about that. We're thinking about properties that are true before the execution of a command and properties that are true after. And these are logical assertions, not states. The other thing that's important is the second bullet point, which basically tells us that we assume termination. We're not proving termination, and that's why we're going to be doing what is called partial correctness. So as I said, the precondition and postcondition are not states, they're logical formulas. And to see that, a lot of people use the assignment rule. With one rule that people formulate looks like that, which makes sense if P is a state, but P is not a state. So if it was a state, it would kind of work like, okay, I start at some state P and then I do the assignment and then I have the same state except now X has the value E. And that's totally wrong. Okay, so it would be something like this. That's totally wrong. So first of all, P is not a state, as I said. The arrow has nothing to do with the map that we usually think of states. So, usually states are like a map from variables to values. It has nothing to do with that. It's just a replacement procedure. So as it says, it means replace all occurrences of X with E. So given that P is actually a logical formula, let's see how this fails. So let's say I start at some state that satisfies x less than 2. So by the way, one other way to think of how a logical formula is different from a state is that a logical formula describes a set of states, the states that satisfy it. So for example, one state is x is equal to 1. That satisfies this logical formula. Another is x is equal to 0, or x is equal to -1. So starting at a state that satisfies this logical formula and then assigning 3 to x, then we get to that, and of course we do the replacement procedure, so we replace all instances of x with e, which in this case is 3. So we get this bogus thing that 3 is less than 2. And in general, the reason this doesn't work is that if we know something about x before the statement, there's no reason why this will be true for e after the statement, because e has nothing to do with x's value, meaning x's value before the assignment, of course. So we can use this intuition of like why this is wrong to just slightly modify the rule into say, okay, well, I'm not going to replace x's instances with e, I'm going to replace e's instances with x. Why that can make sense? Well, because what was true about e before is now true about x. Why? Because x has the value of e. So here's an example. Let's say I start with 2 being less than y, and then I assign x to 2. Then replacing all instances of e, in this case 2, with x, I get x is less than y, which is true. But this rule has a couple of problems. First of all, x's properties may still not hold. So, because its value has changed. So here's what I mean. We start from x less than 1, then we assign it the value of 2. And then we do the replacement procedure, but the replacement procedure says nothing about what you do to x. It only says something that is down to e. So we leave this unchanged, and so we have this wrong thing that x is less than 1, which is of course wrong because now it has a value of 2. Another problem is that we also lose properties of e. Because we're replacing the instances of e, these properties are lost, but they may be true. Here's an example. Let's say that we start with y is less than 1, and then we assign y to x. Then we replace all instances of y with x, and we get this x is less than 1, which is true, but now we lost that y is less than 1. So in general, the rule that works with assignments is this backward rule. It's this rule where we're thinking that if something is true for x after the assignment, then it's true for e before the assignment. That's why it's this backward thinking, because you're thinking from the post-condition, from something that happened after, to the precondition. And that in general makes sense, because we use similar thinking to what we used before. We say that, well, if anything is x, if anything is true about x after the assignment, then that it's only because it must have been true for e before the assignment. So here's an example. We say that, well, if x is greater than 2 after the assignment, then it must be true that e was true before the assignment. Now here are some more derived rules. I mean that you can actually, given this definition that we just talked about of the Hoare triple, you can go ahead and prove these rules like the assignment rule that we just saw. And we're just going to see 2 more rules just to get a better feel of Hoare logic. So one rule is the if rule. This rule essentially tells us that, okay, look, I know, so B here is the condition, and I start with some precondition A. And so it requires 2 assumptions. The assumption is that if A and B is true, A and lower B is true, and I execute C1, I get cap B. And the other assumption is if A and not B is true, and I execute C2, I get cap B again. So basically what this tells us, C1 and C2 are the 2 branches. It tells us that no matter which branch you execute, you're going to get to B, to cap B. And so then we can derive that if I start at some precondition A and I execute the if, then I'm going to get to capital B. Now, as you can tell, this rule is not easy to use in practice because it requires that both branches take you to something common. Like something is true after executing either of the branches, which in practice is not necessarily how if cases work, because many times one branch the then branch is different than the else branch. And another rule is the rule of sequencing, and it's just a kind of an easy rule of transitivity. Here you say, okay, if I start from A, I execute C1, I get to C, and if I start from C and execute C2 and I get to B, then if I start from A and execute both, I get to B. Now we're going to talk about weakest preconditions, and weakest preconditions is a very core concept, and it's also a deep concept. So I'm going to start with some intuitions and terminology. So when we talk that something is weaker than something else, it means, well, of course, we're talking about logical formulas, right? So when we say that the logical formula is weaker than another logical formula, it means it's easier to satisfy. It means more states satisfied. So again, if you think of a logical formula as the set of states it describes, meaning the set of states that's satisfied, then if something is weaker, then its set is larger. And similarly, stronger means harder to satisfy, meaning fewer states satisfied. So here are some examples. X greater than 0 is weaker than x greater than 0 and y greater than 0. Another example is that in general, if A implies B, then A is stronger than B. So of course, what the example we just saw is such an example. Also, another thing is that the weaker the precondition of a triple is, the easier it is to prove the triple valid, because of course, the easier it is to satisfy the precondition. Now, let's go to this definition of weakest preconditions. So this tells us that the weakest precondition for a command, CMD, and a postcondition B, is a precondition such that the Hoare triple, this Hoare triple, is valid. Let's stop here. It tells us that you have a command and you have a postcondition. And now, the weakest precondition, the one thing it tells you is, by computing it, its result basically is a logical assertion that if it's true, then executing command gets you to B. That's a very important concept, so I'm going to say that again. When WPC is true, it means that after executing command, I get to postcondition B. And so you can see it here. It makes this Hoare triple valid. But it's not just a valid precondition. It's also the weakest precondition. That means that any other valid precondition A is stronger. That means that any Hoare triple A command B is valid if and only if A implies the WPC. So this is actually a pretty strong statement. And now here's how we can use that. So we're going to take a step back from theory and we're going to see how we can use this thing in practice. Here are the facts. There's an algorithmic way to compute the WPC for some command and some postcondition B if the command does not contain loops. Given that, and given the definition, how can we verify programs automatically? More specifically, we want to check whether A command B is valid. So the trick is in this definition. If a Hoare triple, like the one we want to prove, is valid, then its precondition must imply the WPC command B. Otherwise, it's not valid. That's what this if and only if gives us here. So the way to do automatic verification is compute the weakest precondition for the command in B and check whether your A implies that. And you can actually use a solver to do that automatically. I would suggest just take a pause here, just make sure that everything up to now is making sense. Again, we're going to use a lot the fact that if WPC command in B is true, then it means that executing command will get you to B. Now let's go to loops and verification conditions. Now loops are kind of hard to deal with because this is the weakest precondition of a loop. And let's just try to figure out exactly what's happening. We want the weakest precondition for some while loop with a condition cond and a body for some postcondition B. So again, we want, what is that we're trying to figure out here, or what this gives us, is it gives us the least thing that should be true, such that after executing this while loop, I get to B. So what is this least thing? Well, that intuitively we get it by just unrolling the loop, or basically by thinking of all the different numbers of iterations that the loop can take. This is kind of what I mean by unrolling the loop. So one way, one thing that is enough to get you to B after executing the while loop is this conjunction here. Because you need to, one way is to know that the condition is false and that B is true already. If you know the condition is false as B is true already, then it means the loop is not going to be executed at all and you're going to get your B. So that's one way. Or another way is to say the condition is true, so I'm going to do one iteration of the loop, but after executing the body of the loop, I'm going to get to the condition being false and B. And the condition being false and B means that the loop is not going to be executed no more, and I'm going to get to B. And again, as I said earlier, this being true, WPC of some command and some condition being true means that after executing the body, I will get to this post condition. And you can just keep doing that, right? So you can say, well, okay, you're going to execute one iteration of the loop. And after executing this one iteration, you're going to get, cond is still going to be true. So you're going to execute a second iteration, but after executing this body the second time, you're going to get to the condition being false and B, so you're going to finish. And so basically that keeps going, kind of an infinite expression. And our problem here is not that much that it's an infinite expression. The real problem is it's very hard to deal with this thing. Because again, to prove that something, as we said earlier, to prove that whether a Hoare tuple is valid, so to prove things about your program, you need to prove that your A, your whatever precondition, implies the weakest precondition. But it's very hard to prove that something implies this monstrosity. So we need a closed form expression. Now, to figure out the closed form expression or what we're trying to do here, let's go back to the definition of weakest preconditions and see some corollaries. The first corollary is kind of obvious. We've already talked about that. Well, if A implies the weakest precondition, then A is a valid precondition for command B. But also there's this sense of transitivity, meaning if I have some X implying the WPC and Y implies X, then Y is also a valid precondition. Why? I mean, that's obvious, because if Y implies X and X implies WPC, then Y implies WPC, therefore through corollary 1, Y is also a valid precondition. So here's how we're going to use that. The idea is to find another condition, which we'll call verification condition, such that the verification condition implies WPC. And then we're going to use this idea of transitivity, such that now, instead of, when we have a Hoare AAA command B, instead of checking whether A implies the WPC, we're going to check whether A implies VC. And the idea is we want something that is easier to deal with. And because of this corollary 2, where basically VC is X and Y is RA, if A implies if A implies the VC, then it implies the WPC too. Therefore, A is a valid precondition. But the idea is we do that without dealing with WPC, which is dealing with VC. So here's why we'll proceed assuming that we have such a VC. The idea is that if A implies the VC, then it also implies WPC, as we said, so the tuple is valid. However, if it doesn't, you can pause and ponder about this. Now remember, with the weakest preconditions, we had this if and only if. Therefore, if A doesn't imply the WPC, then we know that the Hoare tuple is valid. But here, we don't know that, because we don't know if the triple is invalid or if just VC is too strong. But that, for most practical purposes, that doesn't matter. I mean, first of all, it's not that important to prove things invalid. It's mostly important to prove things valid. So that's one. And then second, for many practical purposes, VC is something that you can prove that A implies it. But I want you to take note of the trade-off that we have here. The trade-off is we're going to have a closed form expression. It's something that is easier to deal with. But it's going to be stronger. So it's harder to prove that something implies it. So now the VC that we're going to define is basically, okay, we define it as the same as WPC if command does not contain loops. That's not interesting. The interesting thing is how we define VC. Obviously, just to be sure here, if we define VC being the WPC, then obviously VC implies the WPC. So we just do that to just be dealing with VCs from now on, not WPCs. And it's the same as the WPC if command doesn't contain loops. So the interesting thing is, of course, with for loops, and to figure out how we're gonna define a VC that works or that is a valid precondition, we're gonna take a look at the while rule. Okay, so this is the rule to prove things about while loops. So there's this idea where basically if you know that you have some I that after executing the body of the loop is preserved, then that I is called a loop invariant. And we also say that the body of the loop preserves the loop invariant. Now notice here that we're not talking about any specific iteration of the loop. We're just taking body on its own. That means that I is something that body preserves no matter if it's the first, second, whatever iteration. So if we know that I is preserved into the loop, and then I know that if I start with I and execute the whole loop, then I is going to be preserved afterwards. And of course, the second thing is something I can just infer. That, of course, if I have finished the loop, because again, if you go all the way back to the Hoare triple definition, we assume termination. So we assume here, we don't prove, we assume that the while loop is going to finish, it's going to terminate. So because it's going to terminate, the condition must be false afterwards. So this is the concept of the loop invariant that we're going to use. If you, basically the way to think about this is that if you have a loop invariant, then you can prove things about loops. So here's the verification condition. And again, I mean, we're going to go through that step by step, but what I want you to be thinking here, I don't want you to forget the goal that we want to have here. We want to find some kind of expression that if it's true, or when it's true, if we execute the while body, we're going to get to B. That's what we're getting here. We want to find a precondition that will guarantee us that. So, well, actually, I'm going to skip that. So I'm saying there's three criteria that we should satisfy. First is that the initialization criteria. So I should be true before the loop. Which I? Some I. You should have some I that is true before the loop. If you have such an I that is true before the loop, and you have an I that is preserved in the body or by the body of the loop. And again, let me just, well, actually I'm going to talk a little bit about the bullet points. So just try to understand the text at first, and then we're going to see how this translates to the formula. So try to convince yourselves, or see, I guess, if you're convinced, from the three criteria, from their textual representation, that these three things, if we know the three things, then after executing the body of the loop, we're going to get to B, and then we're going to see how that translates into a formula. So the second thing is preservation. So I is preserved by the body of the loop. And the final thing is termination, which is that when cond is false, we get the post condition B. And my claim is that this should be enough to guarantee us, if I know all these three things, and after executing the body, I'm going to get to B. Why? Well, because look, I know I is true before the loop. I know that I is preserved by the body of the loop. And I know that when the condition is false, meaning when the loop finishes, I get to B. So now I just have to put that into a formula. So of course we have the lonely I here. Here we have a for all that is x1 to xn are the variables that are written to inside the body of the loop. And what I want to have here is basically I want what I'm going to write here to be true for any possible iteration of the loop. So what I say here, preservation, to check preservation, I need to know that when I and cond is true, then this VC is true. And remember, the VC, we use the same reasoning as the WPC. When this is true, it means that executing body gives us I. So saying that this implies that means that this is such that when it is true, if I execute body, I get I. So in this case, it says us that when I and cond is true, if I execute the body, I get I, therefore I is preserved. And finally, I have the obvious thing that I just need that when I and condition is false, I get to B. So hopefully this is convincing to you that it's a valid precondition. Now, of course, we need a proof for that. We need to prove that it's a valid precondition. To prove that it's enough, we need to prove that it implies a WEPC. Now, this proof is not terribly hard, but it's kind of hard. We're not going to do it here. But you will be glad to know that it's in this book, A Science of Programming. Now, I want to say a couple of things here. First of all, a lot of sources online get this whole thing that we just discussed about wrong in many different ways. But there are a few sources that actually get it right. This is one of them. One other source is the book called The Discipline of Programming by Dijkstra. But I think this book, A Science of Programming, is much more intuitive, much easier to understand. Okay, well, this thing it's kind of a side note. You can actually skip it for the rest of this presentation. I do think, though, it's interesting that the fact that VC implies WEPC is true regardless of the I that we're going to use. We can in fact plug in any I, and the problem is that a bad I will probably make the VC being false, and so A just won't imply it. Okay, now let's use this program synthesizer and what we just learned to prove things about programs involving loops. And as you probably can tell, what we're going to be doing is ask the synthesizer to find an I that will make this whole thing being true, or actually this whole, or where is it? Oh, well, whatever. The A implies VC being true, such that we try to find an I that is going to make our Hoare triple valid. So let me talk concretely about that. So here's a Hoare triple. This is not part of Sketch. We're going to be using Sketch, but this is not Sketch. This is just a program in the language of, well, Hoare logic, right? So we have A, command, B. And I'm not going to spend time into what A and B are. It's actually not that important, but whatever. We just want, what we want to prove here is, of course, that this Hoare triple is valid. And the way you do it, normally, as we said, is you just prove that that A implies the weakest precondition for command and B. The program, however, contains a loop, so we have to use the VC. So, goal. Our goal is to prove that A implies VC. So here's the formula. This is our A. We say that for any y, y0, k, whatever, for every possible assignment of variables, if we know that this is true, then this should apply the VC. Now, this is the same VC that we had before with a couple of small changes. So what are the changes? First of all, so here's the original thing. Now, in the original thing, you can see that I is on both the preservation part and the termination part. So it's both here and here. Now we can just pull it out. We can just pull it out all the way out to this parenthesis next to the for all. So this is what I'm doing here because it just makes the much easier to write, basically. Okay, but it's just exactly the same thing. The other thing is, well, of course, here we have this for all that is for y and t because these are the two variables that are chains inside the body of the loop. And the big change is that I is, instead of just writing I, we just write I as a function of the variables, which it should be some expression involving these variables. So that's it. And again, the point here is, okay, we want to check this, but we don't have an I. So what we're going to ask the synthesizer to do is find us an I that is going to make this whole implication true. Now we're going to make our life a little bit easier into doing that by changing the formula a little bit more. So the first thing is that this for all is an issue here. So we want to pull it out, and we want to pull it all the way out to this for all. And you're actually going to see why. So we can do that by introducing two fresh variables, okay, y prime and t prime. And the other thing that I've done is I've expanded the VC. Okay, so remember the VC was, now the VC for things that don't involve loops is the WPC, as we said. The WPC for assignments and sequencing is just the derived rules that we saw. So we just apply the assignment rule twice, basically. And you remember that the assignment rule is just a replacement. So essentially, we just take this post condition and we just do this replacements twice. So we replace y with y minus 1 and t with t minus 1. And that's how we get to this. Of course, y and t have become y prime and t prime because of the two fresh variables I've introduced. So now this is something easier to deal with. And so what we're going to do is we're going to code that in Sketch. So we're going to turn this whole thing into a program. And we're going to ask Sketch to find an I that just makes this whole thing true. So here's how we do it. Yeah, we expand the VC. Okay. So first of all, we deal with the for all. And we put this thing into an if. So an implication is basically an if, right? It's an if that says if this is true, then then this should be true too. The way you do that is you say, well, if this if is true, then for example I need at least this to be true, and I write this as an assert. I say I assert that the inv is true. So again, in this case, it's true before the loop. Now inv is ultimately the function we want to synthesize. Well, for now we'll leave it as a vague function. Eventually we're going to have to actually tell the synthesizer like, look, this is unknown. Just find something that makes it work. Now I want to talk a little bit more about what we're doing here with this for all. So generally the semantics of Sketch, or I guess what Sketch tries to do, is it tries to find, in this case it's going to try to find a function inv that is going to make all the asserts be true for any kind of state. So these are our inputs. And Sketch works in that it's going to try to find something to fill in here such that it works for any kind of input. This agrees with this for all that we have here. So continuing with that, we have another implication here. Now I'm just pulling again the I and the cont together. So I'm saying that assuming that I and cont is true, then I want to assert this. And similarly, if y and the condition is false, then I want this to be true. So again, a Sketch resolution, as we will call it later, is just to find an invariant function that's going to make all these asserts be true for any kind of input. Okay. Now, how do we define inv? We essentially need to define a program space of expressions for the synthesizer to consider. Now, the synthesizer can actually try to figure out something on its own, but we just want to constrain it a little bit. So we basically just say, look, you should return me, or you should just start searching through the program space involving predicates that use the operands of the first argument and the operators of the second argument. So examples of expressions that are part of this program space are things like y plus t less than k, or k equals to y0 plus y. And then we run Sketch, and it actually found a function that works for any kind of input. And this function is basically the invariant we want. So now, here's a cool part. You can actually go and prove that this is a valid invariant, or that your Hoare triple is actually valid, independent of all this VC and WPC. How you can do that? Well, you can use this while rule that we talked about here. And again, this while rule, this is independent of WPC or VC or anything like that. So we can check whether the invariant we found is correct. We just use this in a proof. So here's a Coq proof. That looks quite long. The reason is that it's I use very bare bones features of Coq, which I think is good because it actually is very similar as if writing in pen and paper. We have the Hoare triple here that we want to prove, and here is where I use the invariant that Sketch gave me. Now, we're going to talk about CEGIS, or Counterexample-Guided Inductive Synthesis. So as I said, we're going to look at Armando's thesis. And CEGIS is also interesting because this is how Sketch works under the hood. So basically what we just saw with this program generator, effectively, this thing. The way this works under the hood is the way we're going to describe right now. It's just, we're not going to describe this particular thing, but this particular thing is just syntactic sugar of what we're going to talk about. So first, I want to talk a little bit about inductive versus deductive synthesis, because inductive synthesis is mostly what is used nowadays, but people may be like, okay, what's the alternative? So I want to start a little bit from the beginning, I guess. I think it's interesting. So there are two methods of reasoning. One is deduction, and to use this method you need some kind of soundproof system, meaning, and again oversimplifying, a set of axioms and rules of inference such that they lead you to correct conclusions and how to proceed to prove something, to arrive at a conclusion. Well, you use the rules of inference and the axioms to arrive at the conclusion you want. Example of that is every formal proof you've ever seen, basically. Induction, and I don't mean mathematical induction, is a different way of thinking where you go from the specific to the generic. So you start from a set of observations and then you formulate a general theory that describes these observations. And examples of that is basically every scientific theory that you ever heard of. It's very interesting. Induction is something that is big in philosophy of science, actually. I don't really know why we don't really know much about it in the STEM fields, at least in my undergrad, for example, and other endeavors in education. I haven't really heard of induction, even though it's extremely fundamental to what we do. But induction is something that is very contested in some sense, because we don't know if the conclusions or theories are correct. In fact, there's a whole argument of like what exactly it means to be correct. So you can't prove, for example, that the law of gravity is true. You can only give good evidence for it. Well, another bit of historical trivia that I think is cool is that before the scientific revolution, everyone was using deduction. That was coming all the way from Aristotle and his syllogisms, which is basically the deductive proofs. And he had presented that in his book called Organon, which means instrument. And of course, deduction is the instrument he was talking about. Induction, I think as far as we know, was introduced by Francis Bacon in his book Novum Organon, which means new organon. Okay, so deductive synthesis. It follows a similar philosophy. So you start from a specification of a program in terms of input and output, and then you just create a theorem. And the theorem is basically, okay, I assume that the input predicate is true. There exists an assignment that satisfies the output predicate. So you create this theorem, and then you want to prove this theorem, but you want to prove it constructively. Because if you prove it constructively, you have to give a witness, meaning to prove that such a thing exists, you have to give something that makes this true. And that then lets you to extract a program that actually instantiates that. So basically what I'm trying to say is that I don't want to go too much into constructive logic here, but constructive logic, well, it has the philosophical underpinnings of like, for example, proof by contradiction is not enough. It's not enough to tell me that something exists without giving me an instance of that. So constructive logic was like, you need to give me an instance of that, but this has very practical ramifications for computer science, because proving things constructively, having witnesses, means that you can actually extract programs that from these witnesses. So here's an example. You have some like an input predicate on x1 and x2, and the predicate is just that x2 is not 0, and you have an output predicate on x1, x2, z1, and z2, which is this whole expression, and the theorem you formulate is for all x1, x2, assuming that x2 is not 0, which is the input predicate, assuming the input predicate is true, there exists some assignment of z1 and z2 that makes this whole thing true. Proving this constructively gives you a program that takes you from this to that. The strength of deductive synthesis is that it's correct by construction. Why? Because the program is extracted from a proof. So the program is provably correct. The weakness is that it needs access to a large corpus of axioms, and essentially that constitutes a whole set of rewrite rules that someone has to come up with. And in practice, these rules are many. And so it's harder to automate. Now, inductive synthesis, again, proceeds in a way similar to induction. I should remove this not mathematical here. It was supposed to be for that induction. So the prerequisites here is you have a set of input-output examples, and you're trying to find a program that works, that passes all these examples, right? That gives you the output for the input. And again, you have this question here, well, how do you know this is the program you want? Meaning the correctness of the program is as correct as your input-output examples are. So the strength is that it can be automated in practice much more easily, as you can probably tell, meaning like you can, for example, do a simple syntax-guided synthesis or just search the space of programs for a program that satisfies the input-output examples. You don't need a whole set of rules. But the problem here is that it's not correct by construction. And so usually people couple it with some kind of verification procedure. Now let's go to Sketch. So Sketch uses, what a surprise, sketching. And sketching is a programming paradigm. A sketch is essentially a program with holes. And these holes are to be filled in, but not just randomly. The idea is that you should fill in the holes such that the asserts pass for any possible state. Assuming we're only going to deal with programs having integers. When I find some value to put here such that for any possible x, this assert passes, and of course the obvious answer here is 2. So in general, the problem statement is there an assignment of holes to integers that makes the assert pass for all possible states? There is something important here that I'm gonna keep harping on because it's pretty central. That the assignment of holes to integers, or in other words, the value of a hole, is independent of the state of the program. You can see that clearly in the problem statement because we want to find an assignment that is independent of the state, meaning it has to work for all possible states. But it's very central to know that even though, for example, x and the hole look very similar somewhat, their values, they depend on their values are specified by completely different things. The value of x is defined by the state of the program. The value of the hole is defined by the assignment, and these are distinct. Okay, now to start using some terminology from Armando's thesis. So this assignment is, he calls it a control function of holes to integers. Here's an example program. Here's one assignment that you can have one control function, meaning, now of course the program has only one hole, so the domain of the function is just a singleton. So for the hole with subscript 0, we give the number 2, so this is basically the program. Here's another assignment. Now one thing to notice here is that basically a sketch is a parametric program. In other words, it describes a space of programs. Here's one concrete instance or one element of this set of programs. Here's another. And basically, by specifying the control function, we specify exactly which element of this set of programs that a sketch describes. So, problem statement with this new terminology, is there a control function of holes to integers that makes the asserts pass for all possible states? And the main trick is how to define the semantics of expressions, and in particular of holes, and of asserts. So, we need a primer to denotational semantics, because this is what the thesis uses. Now, don't be scared, denotational semantics, for me, they tend to be very nice, very easy to understand. So here's what we say. This is gonna be usually how denotational semantics are. This is not the way it's defined in the thesis. That's why I've given this denotation here. It's like the subscript S, I don't know, just simple, just to differentiate it from just capital A, which is what we're gonna use for the actual denotation. When I've been talking about the denotation, we just try to figure out the value of an expression, right? So when I say the denotation of an expression is that, it means that the value of an expression is defined as whatever. So the value of, or the denotation for expressions is based on, well, the syntax of the expression and also the whatever state at this very point. So mathematically, again, denotational semantics is such that you map expressions or syntax to mathematical function. So this basically tells us that for every expression, give me a function that, given a state, it returns an integer. The intuition here is you obviously want a different value for this kind of expression, meaning the denotation of an expression depends on its syntax, but also it depends on the state, right? So you want a different value for x when the state says that x has the value 3, and a different value when the state says that x has the value 4. So in other words, what I'm trying to say here is that you're going to be seeing a bunch of arrows going from left to right. And the way to be thinking about these arrows is that the value of an expression depends over these things. Of course, not z, this is just the result. But it depends on the syntax of the expression and the state in this case. So here's a denotation for identifiers. So we say that the denotation for an identifier x, as given some state sigma, is just look up this state, this variable, sorry, into sigma. We assume that sigma is a function from vars to z. Obviously, you can think of this as like a hash map, right, from variables to integers. But again, everything in denotational semantics has to be a mathematical object. That's why this needs to be a function. Okay, so this is just very easy. Hopefully, it should be obvious that this is just equivalent to this, right? Where I say, where of course this is a lambda function, meaning it's a function that takes a sigma as an argument, and then this is its body. So another way to define this is to say, well, the denotation of x is a function that, given a sigma, it just calls this sigma with x as an argument, just looks it up there. But we're mostly going to be using this because this is usually how people write denotational semantics. So here's another denotation for just a binary expression. So here you say it's just basically the value of E1 understates sigma and the value of E2 understates sigma, and we just add them up. Now, one important thing here is for the rest of this presentation, and actually in the actual thesis, we assume expressions don't have side effects, and that's why you can use the same sigma in both cases. In other words, evaluating E1 doesn't change the state, in which case you will need to like get an output sigma from here and use that for the evaluation of E2 and all that. But we have none of that because the expressions don't have side effects, they don't change the state. Okay, cool. Now we want to define the semantics of wholes, and essentially the intuition we want to capture here is that a whole should be parametric on controlled functions. In other words, it should have different values for different phi's. In other words, the way to think about it is that if we look at this definition of A or A sub S here, we don't have enough information to define the value of a whole. Why? Because the syntax of a whole is not enough. The state is not what gives us the value of a whole. The value of a whole is given by the control function. But where is the control function here? So in other words, we want to say here that, look, the denotation that we're going to use has to also be dependent on phi. So the denotation of a whole looks like this. It says that under some state sigma, the denotation is give me a phi, and I'm going to look up the whole into this phi. And what this denotation tells us, by the way, is that the sigma here is unused, which is what it should be, because as we said, the value of a whole does not depend on the state. This doesn't work though. Of course, we need to, now we're returning something that gets a phi, so we just need to put this there, which again, as I said, it just captures the intuition that like our denotation should be dependent on the syntax, the state, and the current control function. And of course, okay, this is, it's equivalent as going up the levels of semantics. Things start getting interesting when you talk about the semantics of commands. Now, usually, the way denotational semantics works for commands is the evaluation of a program P, meaning a set of commands, gets an input state and it gives you an output state. But also, this semantics here is going to be getting an input set of controls and is going to be giving us an output set of controls. And in fact, such that phi prime is a subset of phi. In other words, it constrains the set of controls to only those that make asserts pass for the input state. What I am saying here is that the semantics of sketches is defined as such as I give you a set of phi's, and you, by just evaluating the program, you constrain the set of phi's to only those that makes the assert pass of an input state. In other words, the semantics do some free work here, where I give you a set of phi's and you give me only those that work. And so we'll see how that's great, and how it makes us formulate an algorithm where we're basically going to iteratively keep giving a set of phi's, and the semantics is going to keep constraining that until it leaves us with a set of phi's that works for all possible states. But for now, we need to understand how this constraining happens. So the constraining, this whole effect, is basically through just one statement, which is the assert. Now the assert, the denotation of the assert is very simple. So we say the denotation for the command assert e for some expression e under some state sigma is, so again, we need to give two things back. We need to give a state and a set of controls. We give the same state back. Why is that? Because expressions don't have side effects. So evaluating e doesn't change the state, but the set of phi's changes. We only keep the phi's which make the expression evaluate to 1 under the state sigma. And that's how the constraining happens. So you give me an input state, and by evaluating all the asserts, which is this, I keep constraining the set of phi's to only those that work for all the asserts. So again, a corollary here is that if your program has a bunch of asserts, then the phi's that are going to make it through all of these asserts are only those that work for all of them. We want to find a set of phi's that is valid, but we need to specify what exactly valid is. Valid, intuitively, means something that works for all possible states. A valid control function is one that makes the asserts pass for all possible states. And more in general, a set of valid control functions is a set such that all of the phi's pass the asserts for all possible states. The way to formulate that mathematically is as follows. You say the set of controls capital phi is said to be valid if it is invariant under the evaluation of the program, basically, for any initial state sigma as expressed in the equation below. So we can say up here, the evaluation of a program gives us a tuple, and we just want the second element. This says phi is valid such that over all possible states, evaluating the program leaves phi unchanged. It means that the semantics doesn't constrain it anymore. It means that the set of phi's in this capital phi work for all possible states. Now here's the big hypothesis that gives rise to the CEGIS algorithm. For a given sketch P, which is a program with holes, as we said, it is possible to find a small set of inputs E that fully represents the entire domain of input sigma, such that any set of controls phi satisfying equation 2 will also be a solution to the sketch resolution equation 1. In the original sketch resolution equation, you need to go through all sigmas, all possible states. The hypothesis, which is of course an empirical hypothesis, is that there's a small set E of states such that if your phi remains invariant across those states, then it is invariant through all of the states. In other words, that's what it means, that there's a small set E that represents the whole of sigma. The critical inputs. The hypothesis says that basically, if you can find a small set of inputs, these critical inputs, such that if your phi passes these inputs, then it's valid for all inputs. So, in other words, the way this works is you start from some, say, capital phi 1 that has all possible phi's. I'm going to use some state sigma 1 such that I constrained this phi to phi 2. Okay, so that's going to be a subset of phi 1. And then I'm going to find some state sigma 2, and then I'm going to constrain it even more. So again, these states, because they constrain it even more, they are sort of counterexamples where they make parts of the phi not work. Now, the bounded observation hypothesis says basically that at some point you're going to reach a sigma, say 50, whatever, it's going to be relatively small. such that using this sigma 50 is going to give you back the same phi. And in fact, you're not going to be able to find any other sigma that is going to make this any smaller. And that's what it means that this first 50 states, they completely constrain the output. If it works for this 50 states, then it's going to work for all the states. Now here's how we come up to an algorithm given that. So here's how it works. We start with some sigma random, some random state. And we start with phi 0. It's going to be an iterative algorithm, of course, which has the set of all possible phis. We just evaluate the program with a current sigma and the current phi. And of course, originally, the current sigma is a random state, and the current phi is a set of all phis. First of all, I just want to say, if at any point you try to evaluate the program under your set of lower phis, and you get back an empty set, it means there's no small phi works for this state, which means your sketch is unsatisfiable. Okay, if you find a state such that no phi works for it, then you just can't resolve the sketch. By the way, one other small thing I want to say is that I have this tau empty set here I just saw. You can just safely ignore that. It's just a small extension that is used in the thesis, but it doesn't really change the understanding. Okay, but assuming that you have a set that is not empty, the idea is pick a random small phi. Pick a random element, go through all the possible states and try to find a state that will nullify that or that will invalidate that. So try to find a state under which this current control function makes at least one assert fail. And so how do we know that? Well, we just run the program and you should get back, you pass the singleton set and you should get back the empty set. And here's a trick. That's the sigma I used for my next iteration. So I say, look, I found some sigma I such that an element of the set before doesn't work for, right? I'm going to use that for the next iteration because now I'm going to use that to constrain phi even more. And essentially the hypothesis tells us that at some point you're not going to be able to find such a state. This for loop is going to finish without getting into this if. You're going to have at some point a case where you're going to have a phi such that it works for all possible states, and that's the phi that you just want to return. First of all, hopefully it is convincing to you that if you just forget about all this, and I just give you a phi that goes through this loop without getting into the if, that's a valid phi. We are basically going through the definition. We are going through all the possible states, and we're trying, and we non-nullified, non-invalidated phi, not made the asserts fail for this phi, so therefore it's valid. Then you may have some question like, all right, maybe I picked wrong, right? Because we say pick a random element. Like, okay, maybe I picked a phi that doesn't work for some states, but maybe some other phi in this set works. Okay, that's fine. That's fine because you nullify this phi, cool. So you're going to invalidate it in the next iteration. You're going to be left here, your next capital phi, it's not going to have this element that didn't work. So now you're going to pick randomly again from a smaller set. And again, you may be unlucky of like phi may have like 10 elements, 9 of which don't work and 1 works. And you just keep picking one of the other of the 9 elements. But the thing is, because of this iteration, your set is going to keep getting smaller until at some point you are going to get to your valid thing. If you can't get to your valid thing, you're eventually going to get into this null set. It means you have no valid phi. Now, of course, there are some experiments that we need to have because to see why this works in practice, in particular because the loop, this whole algorithm kind of looks terrible from a complexity perspective. So we have to empirically verify that the bounded observational hypothesis, basically translates to this loop is going to run for a small number of iterations. And this is from Armando's thesis. And you can see they use programs of varying complexity, and you can see that for most programs, they just indeed have a small number of iterations. And now, one thing I want to say here is that you see these bars. These are variance bars, I believe. And I mean, I just don't remember if they're variance or standard deviation. I believe it's variance. And these are basically the variance in the number of iterations through different runs, because there's some non-determinism in the algorithm, right? Like pick the random element. So as we said, you may just pick in a very unlucky manner, where you just keep picking the things that don't work. But eventually, you are going to pick the thing that works, if there's such a thing. We have kind of convinced ourselves, okay, the bounded observation hypothesis works. Like in practice, the algorithm just gives us results. Another thing that's cool is this loop, of course, looks terrible, going through all the possible states. So in practice here, you use a SAT solver, where essentially you just issue the query that like, okay, for all possible states, it will not give me the empty set. And of course, if that's false, it gives you a counterexample, which is what we want here. That's about it. This is the last slide. So the summary of CEGIS is that we define the semantics that allow us to constrain the solution. A small set of inputs constrains the solution, and in practice we use a SAT solver. Also, I guess, well, why not say that? Obviously, this looks terrible too, the set of all possible phi's. So this is actually a symbolic set, and I believe Armando Light has, and in the thesis, he has a lot of information on how you can represent that symbolically. Now, of course, here, when you pick a random element, you do want a concrete element. And so they have a way of like extracting a concrete element from this symbolic representation. Okay, so that was it. Hopefully it was useful. Please let me know in the comments if there's a question, if it's something that's unclear, if there's something wrong. And yeah, other than that, thanks for watching. Hopefully you liked the presentation. Bye-bye.